Okay, so I just want to revisit some of the neural network demos that we did here. So here is one. This is the first demo that I did. Let me run this thing. This is what we had. It's a neural network with one input, one output. X is the input, Y is the output. Um, and it's got two layers, one input. The neuron layer 1 has 2000 neurons and layer 2 has 1 neuron. And this was the sort of program that we wrote to realize this neural network. Okay, so I thought I would show what the network looks like. So this is what the network looks like. So we have X, and that goes to 2000 neurons here, and then the 2000 neurons have 2000 outputs, and they go back to one neuron, which gives the one output Y. So X goes to Y, one input, one output. Okay. So, and because this has 2000 neurons, this layer has 2000 biases. Okay, so num neurons layer 1 biases. That's what we have here. And 2000 weights because, well, each edge will have essentially a weight in this network. So there are 2000 edges here, or 2000 sort of lines joining a neuron to neuron. So we'll have 2000 weights. Okay. And then similarly, another 2000 weights, and then one bias because there's just one neuron here. Okay, so that's for the layer number 2. Here we are actually doing linspace -2 to 2 for X list. This, I just want to make clear, is just for plotting Y versus X. We still have only one input and one output. And then what we are doing here is just essentially evaluating the value of Y for different values of X so that we can plot the function. So I found it easier to actually, rather than put it in a loop like this, where the neural network function is sort of written in this main program. Instead, it's convenient, perhaps, or maybe clearer, if you wrote a separate function like so, something. Something 1D, 2-layer, or something like that. And the input is X, the output is Y. And then, of course, we also need these variables: bias layer 1, weights layer 1, bias layer 2. I'm going to the next line. Okay, so those are all the inputs. I'm going to store this in this thing. And then this is basically X. And this is basically Y. Okay, so we get X. There are all these constants which allow us to transform X to Y. One number input, one number output. Okay, so what we can do here is just, of course, go exlisify equals neural network, blah, 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 all this stuff. This is Y list of I. Okay, so what we're doing here is just evaluating Y as a function of X. Y is a function of X for different values of X, and plotting that. So if we do this, we'll get the same kinds of plots. Okay. But sort of more importantly, we can take this function and stick it in the command line, we don't have X here, but if we and then we can give whatever input we want. We can say 2, y value is that. We can say 2.3, y value is that. We can say -5, 4. So we give some value of x, we get some value of y. So this is what we mean by single input, single output. And then just to be clear, here we are evaluating that relationship over and over again so that we can actually plot it. Okay, but the function itself just takes one input and one output. So this part is the neural network part. Similarly, we can, so that's this function, okay? Similarly, we did something with 2 inputs and 1 output, and then plotted it with surfaces. That's this thing. Again, I'm going to take these pieces and convert that into a function, just to be clear. So this is 2D, 2-layer, or 2-input, 2-layer, something. And I'm going to say x1, x2, 2 inputs. And then, of course, we have these weights and biases. So weights layer 1, bias layer 1, bias layer 2, weights layer 2, and then let's save it at that. And then this is just one output, so we're still going to say y here. And input is just x1 and x2. So if you want some function or program to be better indented, should do that. Okay. Then this is just y. Or we can just do this equal to y here. And delete this. Okay. So we get the 2 inputs, and then these are all just constants that gets propagated through the network, and we get y. 2 layers. Okay. Okay, so let's do that here. And then here we just have y grid of I comma j equals, this is x1 grid of I comma j and x2 grid. So we are evaluating this neural network at a variety of x1 and x2, and then doing a surface plot here. That's what we're doing. Okay, so we can, if we want, do this instead if it's a bit more clear. Okay, so if I run this thing, we already saw surfaces like this and sort of classification kind of like this. Just goes to show that having a couple of layers, I guess this just has 50 hidden layers, not 2000 hidden layers, but if you have 50 hidden layer neurons as opposed to 2000 hidden layer neurons, And then if you do make it 2000, we get these incredibly spiky surfaces. Kind of looks remarkable. Okay, you can zoom in here. Okay, so that's the main thing I want to do from last time. Essentially wrap the neural network in a single function so that it takes the two inputs, and these things are just other additional inputs that are kept constant. Okay, just to indicate that this is just two inputs and one output. Okay, so again, we can say this is y, the one output, and then we can do that just to make it clear. Okay. And again, because we're just using random biases and weights, we get, each time we run the program, we get a different pattern here. And again, the goal is to tune these biases and weights in a manner that the function between some inputs and outputs is whatever we want it to be. And that's what we're going to do next. We're going to use these techniques to do the MNIST problem better.